Hi, welcome to Act 1 of Hijax. This is Lecture 1, High Automatic Differentiation. So this is the first of 5 lectures in Act 1, which are all about the fundamentals, some sort of basic elements of JAX as a programming paradigm and the kind of things, the kind of tools that you have for doing machine learning in JAX, apart from the acceleration, just how to write your programs with JAX arrays rather than NumPy arrays. And the first step of this tutorial is to learn about a fundamental function transformation called jax.grad, which does automatic differentiation, the sort of the heart of deep learning in JAX. And so we're going to explore automatic differentiation through the lens of a tutorial on implementing a student-teacher linear model. This is one of the simplest machine learning models that you could have, one of the simplest examples of gradient descent, which is the core algorithm in deep learning. And so in doing this, we're going to get a chance to explore jax.grad and get to know really our first function transformation in detail. And we'll also get to have some more practice with just general JAX array operations as well. And so I'm here in the Hijax repository in the Hijax virtual environment. And I'm going to go into the lecture 1 directory where I have this Python script train.py. And so you can follow along with me by getting this script from the repository. And so it's just got an overview of the topics today. We're importing time for sort of pacing our output so that we can see an animation, Tyro for controlling it via the command line like before, matplotlib for doing some terminal-based animation, and JAX typing for annotating our array operation, or our array shapes. And of course, just like last time, we've got JAX and JAX NumPy imported as JNP. The rest of this script to start is very simple. We're going to code the rest all line by line. What we've got is a main function that sort of just has these hyperparameters of how long we want to train for and what the learning rate is going to be. We'll fill this in. And then we have a helper function that I've put in for visualizing linear models. So it's going to take 2 models, I'll explain what these are in a moment, and some other information about training, and then show, it's going to basically use matplotlib to do a scatter plot that's going to show us these lines. And so we'll get to that. We'll also have to fill in some of this by ourselves. So let's get right into the actual coding of the teacher-student thing. And so first I need to define my teacher and my student, which are going to be sort of linear models. And so they're going to have each 2 parameters, one sort of bias, one weight parameter and one bias parameter, or one slope parameter and an intercept parameter. This is just going to be a very simple single-dimensional linear model. So let's start by defining the student, or actually we'll start by defining the teacher. And so the teacher, let's call it W teacher. So W for just weight is commonly used for parameters in deep learning. And I'm just going to hard code this as a JNP array. And I want this array to have the values 0.5 and negative 1.0. And so this indicates, what I'm going to mean by this is that we have a slope of 0.5 and an intercept of negative 1 on the y-axis. And then I want to do the same thing for defining the student. And so the student parameter is going to be another linear model, another 2-parameter array, and that is going to be, I'm going to give this the parameters. I want a slope of negative 1 and an intercept of positive 3.0. And I'm making sure to use floating points here to fully type out the point, because otherwise by default JAX would give us like an integer array here. But another alternative would be to specify the data type as floats. Okay, so this tells us the parameters of the models, but just because we know the parameters doesn't mean we know what to do with them. And for that, we're actually also going to need this in order to visualize these models. And so the visualization function needs to have a way to kind of find out what the outputs of these models are for a given input. And I would say that in general, a deep learning model is kind of defined by, first of all, what is the parameter space? And like what is the particular parameter of this model? And then second, how does that turn into the behavior of the model, the input-output behavior? And so I'm going to implement a function now called forward, sort of named after like the forward pass in deep learning. It's going to take an arbitrary 2 floating point array, so this float array with just shape 2. And it's going to take a batch of inputs. We'll later use VMAP to make writing batch code a little bit easier, but for now we can do this one by hand because it's super easy. And the output is going to be, so this is like the x values, this is the parameters of the model, the output needs to be the y values, the outputs of the model. It's just a linear model, so it's just taking one scalar as input. It's just going to give one scalar as output because it's just one dimensional. And so that's going to be also for each input, there's going to be one output. So it's just going to be the shape of the batch size. And how we can do this is we could just take the W and say, okay, well, in there I've got a slope and an intercept, or a weight and a bias. I just want to extract those and maybe say, let's call the slope A and the intercept B. And you can just use unpacking to do this in JAX, like in NumPy, as if it's just a tuple of two numbers. But in general, you might want to use some indexing or something like that. And then we're just going to actually calculate y based on x. And to do that, we're just going to take the slope, multiply it by the input, and add the intercept or the bias. And this expression should be very familiar to people, just basic maths of a linear model. And so once we have this forward function, we now have defined our linear model and these two parameters. We can now visualize what they sort of look like in terms of the outputs. So to do that, we have to take a quick look at this visualization function. So it takes some inputs, the parameters of the models, and also some information about where we're up to in training. And it's going to create a plot on some axes with scatter plot. Oh, actually, it might help if I just call this right now. If I viz W teacher and W student, and for the step, I suppose I can just use 0, and the loss, I can just use, I don't know, jnp.inf, because we haven't started yet. Maybe there's infinite loss. I don't know. It doesn't really matter. And then this function, by the way, returns a plot, and so we're going to have to print to get that plot onto the terminal. That's how matplotlib is going to work. And so if I just run this code now, okay, I've made a typo, but if I fix the typo, this should be a colon instead of a comma. If I fix the typo, then I can run and we get, infinite loss, step 0, but here we have sort of a blank axes. And I want to basically try different inputs and different x's and get the y values and plot them with a scatter plot. And so to do that, I just need to add some lines to my series here, to my scatter plot here. So I want to add one for the teacher and one for the student. So for the teacher, we want to add a series where I've already got these x values calculated, so just using JNP linspace to get some evenly spaced values between -4 and 4, which is the range on my plot. I'm going to get 80 of those values. That's going to be my batch. And I want to use the forward function we just defined to pass these into the teacher model, W teacher. And, oh, I've noticed a problem is that I put these in the wrong way. So I guess I better say this is actually the student and then the teacher, because that's the order that we're expecting them in here. Student and then teacher. I normally try to use the full names of arguments to avoid this kind of problem. But anyway, this time I'm glad I caught it. So we're going to put the teacher here, and then we're going to use these x values. And this is going to give us the y values. And so matplotlib for a scatter plot will let you say what is a vector of x values, what is a vector of y values, and what color would you like it to be. And I want the teacher to be in cyan. So then we can define the student as well in the same way. So we can just say x forward w forward W student and X, and then I'll make the student magenta. And now I should be able to visualize both the teacher and the student. There we go. So there's the slope 0.5, intercept -1, and slope -1, intercept 3 going here. So that's great. Okay, so our job now is to basically take this and train this student to match the teacher. And so I said we're going to be doing teacher-student learning and gradient descent in order to make that happen. So what does that look like? First, I'll give just a conceptual reminder of gradient descent for teacher-student learning and what that's going to look like on the whiteboard. So here I have a plot. It's basically the same as what we're seeing in the code. I have the teacher represented here as one line and the student represented as another line. Gradient descent is normally about sort of having some loss function defined on the outputs of these models and then taking steps of the parameters of the model that you're training according to which direction is going to reduce that loss. And so here, in order to compute the loss, I need to basically try some different inputs. So I could just take various inputs, like this one, this x value here. I can put it into the model, and my teacher is going to give me, I can put it into both models. My teacher is going to give me one value. My student is going to give me another value. And I could say that I could take that difference and I could square it to make sure it's positive, and then say I want that to go down. So I'm going to do gradient descent on that amount. And that will, in general, change the parameters of the student so that this point on the line is closer to where it should be. And so that is basically what we're going to do for a range of different x values. So let's get back to the code and get that happening. And so first I might define this loss function. It's going to take w student. I guess I can define it like this. So it's going to take, again, a floating array of length 2. It's going to take also w teacher, float array of length 2. And then I want to take the, well, that should be fine, but I want to return a floating point number to be the output. Just a general Python float will do it for the typing, but I guess it's actually going to be a jax scalar. And so in order to do this, what I should do is I guess I should get the values output. Oh, I guess I need some inputs first. So I'll do the same as we did in the visualization. I'll use jnp.linspace. Maybe between -4 and 4, and maybe 80 points is plenty. And then I should get the y's from the student. And so I'll ask the student for these. I'm going to use the forward function that we defined. So I'll pass it in the parameter of the student, if I could spell, and the inputs, and it should give me the outputs. And then I can do the same for the teacher. And then I'm going to get the, so I'm going to use the forward pass again, teacher x. So then I want the differences between these, or which you could call the errors. So the errors are going to be y teacher minus y student. And this is going to be an array of 80 numbers that represent how different these outputs are for each of the x's. I better get the squared errors so that these are all positive numbers. So that would just be errors. It's just an array, so you can just like raise it to the power. This will do an element-wise squaring operation, just like in NumPy. And then I want to take the actual loss to be the mean of the square of the errors, or mean squared error. So let me just return this straight away. We'll do jnp.mean of the squared errors. And that should give us a single floating point scalar, jax scalar, and return that as the loss. Okay, so once I've got the loss, I'm ready to do my training loop itself. And so let's get ready to do that. So training loop. I have configured the number of steps that I'm going to use as 400, so I better use num steps, this variable. So for step in range, let's actually call these steps, we've already used step 0 being before. Let's start counting from 1, and then we've got to go to num steps plus 1 so that it includes the 400th. And then we know that we could evaluate the loss. That's one thing we could do. So we could say loss is equal to, I've just used L for loss, because we used the loss for the name of the function. We're going to need to pass this w student and w teacher. And then that will compute the loss. But what I actually need is the gradient of the loss, right? So that I can take a step of gradient descent. And so to do that, I need really not this loss function, but a function that computes the gradient of this with respect to the student parameters. And so this is where jax.grad is going to come in. So I'm going to take jax.grad of loss, and this is going to give me a function that I could call something else. If I want here, I'm just going to do it in line. Jax.grad is going to give me a function that takes this function, takes the derivative with respect to the first parameter, which is assumed to be some kind of floating point array, so we can take a derivative with respect to it. And then it's going to compute the derivative of the output with respect to that parameter and return that. And so this function here, maybe it's clearer if I do define this as a function actually. I'll call this the grad function. Grad function is jax.grad loss, and then I can get the gradient itself by calling the grad function with the inputs that I want to evaluate it at. So w student and w teacher. And then after I compute this, I'm going to have the gradient that I want. And this is how I need to do my update to my student model. So that's computing the gradient. And now we're going to apply the gradient. And so to do that, this is just a vector addition operation. So I just need to do something like w student plus equals, or actually I guess it's gradient descent. So it's minus equals the grad, g. But actually that will be in general like some pretty big numbers here, especially we're dealing with some big differences here. So what I want to do is I want to make sure I have a learning rate to make sure that it is going to be stable. And also, this is also not quite ready because remember, we can't modify jax arrays. We can't, and this counts as a modification. This is an in-place operation. And so what we would need to do instead is we need to compute a new value, w student minus the learning rate, And then this expression will go and override the old value. So we need to make sure we're creating a copy of the W student array rather than modifying the existing one, because JAX arrays are immutable. So this should work, and this should basically be enough to get us the learning that we want. I'm just trying to think if I missed anything. I guess we'll find out when we run it. But before we run it, we want to make sure that we can see what's happening. And so I'm just going to add a little bit of code here to compute a new plot that is going to be it's going to be using this vis function, which remember takes W student, W teacher, make sure we get those the right way around. The step is going to be just step, and then the loss is going to be L. And then this should give us a plot, and then I'm doing this so that I can print the plot, but I want to print it in a special way. I want to basically do a thing that is going to overwrite this previous plot, and so this is just a bit of Python magic. If you type hex 1b to give us ANSI escape code, and then you say I want the plot's height. So matplotlib have this like height variable or property that you can access, and then that will basically say this is an ANSI escape code that says to the terminal, go back a few lines, this many lines, plot.height lines, and then start printing from there instead of printing from where you're up to at the moment. And then I'll print the plot, and that will then print the plot over the previous plot, and so we'll see a bit of an animation. And to make the animation a little bit more visible, I'm also going to time.sleep 0.02 so that I get 50 frames a second. Now, if everything is set up right, Python train, here we go, beautiful. So you can see the loss is going down as the steps are going up. The student is getting closer and closer to the teacher until by about step 400, it perfectly matches at least to the resolution of matplotlib. And that is gradient descent, teacher-student learning. So that's the successful demonstration. It's not doing it as I kind of expected. So maybe I missed something. Oh yeah, I actually missed the ANSI code that you need to put an A there, my bad. Let's do this one more time. Now we see we've got our prompt there, and this is an actual animation rather than like a flip book scrolling past. So that's what I meant. Sorry about that typo. But yeah, it's satisfying anyway to watch it a second time. Okay, so one more thing I want to sort of show before I show you the challenge is I want to show you that this jax.grad, it's kind of annoying that if we wanted the loss, we had to call the loss function with the arguments, and then we also had to compute the gradient and call the grad function with the same arguments again. And this is a pretty common task to want to do both of these. And JAX has a way to kind of save some keystrokes and also some computation where possible, because this is really doing like this grad function is actually doing like a forward pass and then a backward pass. And so really we've done the forward pass twice here. So we can save some keystrokes and some computation by combining these. And we want to use the JAX value and grad transformation instead of the jax.grad transformation. So this will give me a loss and grad function, which if I call that one instead loss and grad function, that will give me a tuple of outputs where the first one is the loss, so I no longer need to compute the loss separately. Now it will do the forward pass, compute the loss, then do the backward pass to compute the gradient, and then it will return them both, the loss and the gradient, and so I'll have them in one go. And that's a bit more efficient, and it's a common pattern that you'll see in JAX code. While we're talking about efficiency, I should note that actually performing the automatic differentiation 400 times is a bit of a waste, and you would, in practice, you would actually do this, and then you would compile it so that you sort of bake the automatic differentiation into the compiled version of the program. But we're not going to worry about performance until we get to Act 2 and start talking about JIT again. For now, this is such a small model that it's running in a split second anyway, and we're getting out the sort of output that we want fast enough for us because it's a super small model. And so we'll leave it at this. I think this is a satisfying sort of place to leave it. We've done everything we wanted. We've learned about, we've learned a few more JAX operations. We've had a reminder of some of the ways of working with JAX arrays and immutability. And we've learned, importantly, this jax.grad or jax.value and grad transformation. And so I do want to leave you with this. So let me show you. This is jax.grad, and then here was jax.value and grad. I was just looking this up beforehand. And you can use the JAX documentation, which, as a reminder, is like excellent, very comprehensive, very detailed explanation of all of the arguments. And it explains basically what I explained in that this takes the derivative with respect to the first argument of the function. I actually don't know if I said that. So we can read about it here. So jax.grad takes function to be differentiated, and then by default, the argument that we take the differentiation with respect to is the 0th argument, or the first positional argument of the function. And so that's why we were getting the derivative with respect to the student rather than, say, the teacher, which was also part of the loss function, one of the inputs. So but we only got the gradient with respect to the student. And that brings me to the challenge, which is to say that your challenge is to rewrite this code in a way that takes the derivative with respect to the student and the teacher. I mean, we often say in teaching that sometimes teachers learn as much from their students as the students are learning from the teachers. And so we could put that into practice in our code, in our teacher-student learning setup, by taking the gradient with respect to both the student and the teacher, and then doing a gradient update on both of them. And what you should see by the end is that this code should have both lines converging to each other, rather than just the student coming to a stationary teacher. And so that could be a bit of fun, a bit of a nice challenge for our first Hijax lecture of Act 1. And so good luck with that, and I'll see you for the next lecture.